Welcome to the AI Research Roundup. I'm Alex. Today we're looking at a paper trending on X published on January 8th, 2026, just 2 days ago. It introduces a new defense system for large language models that achieves a massive 40 times reduction in computational cost, while keeping false refusal rates down to just 0.05%. The paper is titled, Constitutional Classifiers ++, Efficient Production-Grade Defenses Against Universal Jailbreaks. And, as we'll see later, the robustness results from over 1,700 hours of human red teaming are really impressive. Alright, to understand why a new system is needed, Figure 1 illustrates vulnerabilities in last-generation defenses. On the left, Panel A shows a reconstruction attack where a harmful request is fragmented across harmless code snippets, tricking the model into reassembling it. Then, on the right, Panel B demonstrates an obfuscation attack using riddles and metaphors. Terms like winter's breath confuse classifiers that only look at the output in isolation, because they miss the dangerous context established in the prompt. So, to address these vulnerabilities efficiently, the researchers analyzed the performance of linear probes. Figure 2 breaks down the results across 3 key design choices. First, in Panel A on the left, the best probe achieves a low attack success rate, effectively matching a small external classifier while outperforming the extra small version. Then, Panel B in the middle shows that combining logit smoothing with softmax weighting is critical, driving the success rate near zero. Finally, Panel C on the right confirms that using all model layers provides the strongest defense. Well, Figure 3 demonstrates why combining these linear probes with external classifiers is the winning strategy. Panel A on the left reveals that the probe S ensemble achieves the lowest attack success rate, significantly outperforming purely external ensembles. Then, Panel B explains the mechanism. The probe and external classifier show lower rank correlation, meaning they make independent errors and cover each other's blind spots. Finally, Panel C maps out the efficiency gains, where the green curve shows the system maintaining top-tier robustness while slashing compute costs by nearly 100 times. Okay, Table 1 summarizes the final performance metrics across the different system generations. The first row establishes the last generation baseline with 100% compute overhead, while the exchange classifier in the second row improves robustness, dropping the vulnerability rate significantly. It unfortunately spikes the compute cost to 150%. However, the production-grade system in the bottom row changes the game completely. It achieves the lowest vulnerability rate of 0.005 while slashing compute overhead to just 3.5%, effectively solving the efficiency bottleneck. So Figure 4 expands on those summary metrics with a detailed breakdown across 6 panels. In Panel A, we see the production-grade system, represented by the brown bar, achieving the lowest vulnerability discovery rate. Panel C reinforces this robustness, showing that it takes red teamers nearly 30 hours just to find the first flaw, compared to under 5 hours for the last generation. Finally, Panel E visualizes the massive efficiency gain, where the compute cost for the final system is negligible compared to the resource-heavy exchange classifiers. Alright, while the previous results highlighted the system's overall robustness, Figure 5 validates the specific technical choices behind the linear probes. Panel A compares different loss functions, showing that the smoothed softmax approach on the far left yields the lowest attack success rate, significantly outperforming the cumulative maximum baselines. Next, Panel B examines the sliding window size used for smoothing. We see a clear pattern where a window of 16 tokens provides the optimal defense, since the error rate rises if the window is too narrow or too wide. So, Figure 6 investigates the impact of weighting when combining these different models into an ensemble. In Panel A on the left, mixing 2 external classifiers shows little synergy, as the curve simply transitions from the weaker model's high error rate down to the stronger ones. However, Panel B in the center reveals a massive benefit from mixing types. When combining the linear probe with the small external classifier, a deep valley appears where the error rate drops below either standalone model. Panel C on the right confirms this complementarity, demonstrating that internal probes and external classifiers cover each other's blind spots. Wrapping up, 2 takeaways stand out. Effective AI safety doesn't require massive compute overhead, and combining internal probes with external classifiers creates a much stronger defense than either alone. This approach finally makes robust protection practical for real-world deployment. That's it for this episode of the AI Research Roundup. I'm Alex. Thanks for listening.